Hi friends, myself Arun, Assistant Professor, R&D Engineering College. In this Tiva C series Launchpad Programming Workshop, now we are going to enter into the Lab 4. This Lab 4, we are going to discuss about how to programming with ADC. So, the Tiva C series microcontroller, that is ARM Cortex M4 microcontroller, consists of inbuilt analog to digital converter. There are two inbuilt analog to digital converter is available, that is ADC 0, ADC 1. So this analog voltage or analog value is given as the input to the ADC. The output, it produces the digital value. So here, in this board, we have the option of potentiometer. This potentiometer has given the various input voltages when we rotate the knob, and this various input voltages is given as the input to the ADC. Then that ADC convert corresponding analog value into digital. That digital value we have to display in the 7 segment display. So now we are going to use potentiometer, inbuilt ADC, and then 7 segment display. So this is the internal circuit diagram for ADC experiment. So this is the potentiometer. This potentiometer connected to the port pin number PD3, GPIO port D pin 3, and output pins we are going to select PE2, PE3, and then PE4. This PE2, PE3, PE4 is given to the 7 segment display. There are 4 7 segment displays are available. These 7 segment displays are connected to the decoder 74HC95, that is shift register. So each and every 7 segment display is responsible to uh, show the value 0 to 9, right? 0 to 9. So now we are using the peripherals PD3 and PE2, PE3, PE4. So as usual, this is our flow chart for this ADC experiment, that is system control clock set. First I'm going to control the system control clock. So for this syntax is system control clock set, already we know what is the full line of this system control clock set. Then I'm going to enable the ADC channel and port E, port D, because here we are using PE2, PE3, PE4 and PD3. So enable port D, port E, and then ADC channel, and set PE2, PE3 as the PFI as output, PD3 as the input, and read analog value. So read analog value from the potentiometer. So we need to enable the ADC channel. For enabling the ADC channel, we are going to use the two syntax: ADC sequence configure, ADC sequence step configure. Then we have to start the conversion, analog to digital conversion. This type of analog to digital conversion used in this ADC, successive approximation register type ADC. So in this SAR type, we need to convert analog values into digital value. So you have to start the conversion and end the conversion through the interrupt of ADC channel. And then conversion value sent to 7 segment display through the shift registers. And we have to vary the analog values in the way of vary the potentiometer. We'll see the output value in the 7 segment display. So let we enter into the program. So first you have to, as usual, you have to write that header file and variable declaration. So as usual, what are the header files you have to add it? You have to type the header file including adc.h. You have to add one file, one name, on a library file adc.h, because we are going to use the syntax ADC sequence configure, ADC sequence step configure. These syntax are available in the adc.h. Then I'm going to load the value. 0 to 9 into the 7 segment display. For that, I'm declare the variable void shift out 1 unsigned character string. I have to move the string value 0 to 9. Then into main void, and the remaining variables I want to declare, that is unassigned integer 32-bit value. What is the value? Unassigned integer 32 ADC 0 value. I'm going to use ADC 0 because I already mentioned you there are two ADCs are available, ADC 0 and ADC 1. Here I'm using ADC 0. So unassigned integer 32-bit UI 32 ADC 0 value, get the value 6, and unassigned integer 32-bit UI 32 temperature average, temperature value. See, these are the variable declaration only. We can use any variable here, but all the variables are unassigned integer 32-bit. Then value C, unassigned integer 32-bit number 1, number 2, number 3, number 4. So I have to declare 4 numbers because I used 4 7-segment display. Each number has to vary 0 to 9. So these are the variable declaration. These variables I'm going to use in the main program. So as usual, the first line system control clock set, you know the meaning of system control clock set. So start from 16 megahertz, and main oscillator PLL, you are using system division 5, you will get the system control clock. Then I'm going to enable the system control peripheral enable GPIO E and ADC 0. Okay, GPIO PE1, PE2, PE3 I think, and ADC 0. And in this GPIOE, what are the pins are output pins? Pin 2, pin 3, pin 4 are the output pins. So GPIO pin tech, GPIO output, GPIO port E base, pin 2, pin 3, pin 4. So these are the peripheral GPIO port peripheral enable of PE, that is port E. And how to enable the ADC 0? So ADC 0 we have to enable through the ADC sequence configure. Like how we are using how we are enabling the peripheral by using GPIO pin type system control peripheral enable. Like we are used to syntax for enable the ADC 0 through ADC sequence configure. So ADC sequence configure, what is the base? ADC 0 is the base. In this ADC 0 base, comma 1, comma ADC trigger processor, comma 0. So no need to worry about what should be written in the bracket. In the Code Composer Studio, you have to type that syntax ADC sequence configure. It shows us the template. In the template, we have to type the value. Let me tell you, when we are using that Code Composer Studio, I have to tell you these lines. And ADC sequence step configure, ADC 0 base 1 comma 0 ADC control channel 4. Here I'm using channel 4. Each ADC 0 has 6 channel I think. So in this channel we are using channel 4. Similarly, ADC sequence step configure ADC base 1 comma 1 1 comma 2, remaining sentence are same. So sequence step configure, the syntax format is ADC 0 base 1 comma 0 ADC control channel 4. Similarly 2 3. So 0 1 2 I'm using used for control. Then ADC sequence step configure ADC 0 base 1 comma 3, that is 0 1 2 3. So 4 times I'm going to do the conversion. So ADC 0 base 1 comma 3 ADC control channel 4, then ADC control interrupt enable, then ADC control end. Right. So the conversion start from once you have to enable the interrupt and start the conversion, and we have to give the command control end. We have to stop the conversion. To start the conversion, end of conversion, we have to use the syntax ADC control interrupt enable ADC control end. Then ADC sequence enable ADC 0 base 1. Then I have to move this digital value into 7-segment display. So each 7-segment display, I have used 4 7-segment display. Each 7-segment display has to display the value 0 to 9. So this is the FC for, I think you have to in the 8 LEDs, you want to display the 0. What are the LEDs should be on? So you have to make mark that value, you will get corresponding hexadecimal value FC. Similarly, I have to use that hexadecimal value for the corresponding 0 to 9 in 7-segment display. FC 60, DA F2 66, B6, BE, E0, FE, F6. So this 0 to 9 use the value. So not only this experiment, any experiment you are using a 7 segment display, you can use this values hexadecimal standard common hexadecimal value for display the value 0 to 9. Then start the program. While one ADC interrupt clear. First you have to clear the interrupt. In which interrupt you have to clear? ADC 0 base 1. Then ADC process trigger. You have to trigger the ADC processor, ADC 0 base 1. First you clear the processor, then trigger the processor. And while ADC interrupt status false, while not of ADC interrupt status false, we have to wait for some time, call the delay. That is, these loops are wait for some time. Then automatically ADC sequence data get, you have to enable. So ADC sequence data get ADC 0 base 1 comma 1. This is unassigned integer ADC 0 value. This ADC 0 value will get from the potentiometer. Then unassigned integer 32 temperature value C, temp value C, it is equal to unassigned 32-bit ADC 0 value of 0. There are four values we have to mention in the array 0, 1, 2, 3. Then first number is equal to this value UI 32-bit temp value C divided by 10. Similarly, UI 32 temperature value C is equal to value divided by 10, that is number 2, right? And similarly, the same lines are repeated for number 1, number 2, number 3, and then number 4. So you have to use the value. This value is equal to what value you have to get in the number 1, that will be divided by 10, and this is number 2 equal to 10. Similarly, number 3, number 4, same line repeated for number 3 and then number 4. Then you have four numbers after converting the analog to digital. These four numbers you have to given to the shift out registers, that is shift out 1, a number 1, a number 2, a number 3, a number 4. Finally all the displays are 0 0, then call the delay. So now conversion process is over. That is how from conversion analog into digital conversion is over, and the digital value get into the array of A of 0, A of 1, A of 2, A of 3. That is A of number 1, A of number 2, A of number 3, A of number 4. Then the next part of the program is you have to enable the port E lines, because we are used PE2, PE3, PF, PE4. Just we have to write that port, right? So how to write the port for this is continuous operation, right? So that's why I have to use the void shift out unsigned character string, unsigned character j equal to 0, check j equal to 0, j less than 7, j plus plus, and GPIO pin right port E base GPIO pin 3 comma 0, pin 4 comma 0. Initially you have to move the value 0, then check the string value 1 less than j. If check, you have to check the values you get or not, the values get into the array or not. So if check values available, just GPIO pin right port E base GPIO pin to 0x04. I already mentioned the previous videos. You want to enable PE2 means the value is what? 0 1 2. 2 is 1 means 4, hexadecimal 4, that is 0x04. And 3 you want to enable means 0x08. Fourth pin means 10. Fourth pin means what? Fifth bit, so 10. Similarly, you have to move port E base pin to 4, else pin to 0, pin 3 8, pin 4 10. So why I have to move pin 2, pin 3, pin 4 value? Go back to check that diagram, because pin 2 connected, PE2 connected to data select, pin 3 connected to HCHP, PE34 connected to STCP. This was shift register input. So we have to first you have to if PE2 enable, send the data. If PE2 is not enabled, send the clock signal. So that is the way we have to write the data into the corresponding port E pins, right? So that's all about the program. Then we have to copy the program and paste into Code Composer Studio. Then we have to check the output. So already I have to take the program into the Code Composer Studio. I will tell you how to remember these values. So no need to worry about this. Just you have to type ADC sequence ADC sequence configure. Just you want to know the syntax, then it will show you what is the value. Just go to the cursor here. So the syntax format is ADC sequence configure unassigned integer 32 bit, unassigned integer 32 base. What is the base? ADC 0 is the base. Then sequence number 1, I'm going to use number 1, ADC 0 base number 1. Then unassigned integer 32 bit trigger. What is the trigger? ADC trigger processor. Then priority is 0. So this is the syntax format. So once you type ADC sequence configure, it show like this. Then you have to remember that what are the ADCs we are using. So that is ADC 0 base, this value is 1, and trigger processor, this value is 0. Similarly, here just I have to type ADC sequence step configure, open bracket. Just have to check the syntax format. ADC sequence step configure unassigned integer 32-bit base. What is the base? ADC 0 is the base. Sequence number is 1 and step number is 0. Then what is the channel configuration? Channel 4 configuration. So 0, 1, 2, 3. I have to use 0, 1, 2, 3. So this is the way we have to type that corresponding ADC 0 values. Right, I hope you understand the program. Right, so any doubt in this program or anything you want to know, just type in that Q&A box. I will give you answer. Right, then I have to save the program and build. I think no errors in the program. Then as usual I'm going to debug the program. So once you successfully debug, just click this button. Then your program running in that microcontroller, just go back to check that board. Yes, once you install that program in the microcontroller, TM4C microcontroller, right? So immediately your 7 segment display turn on and show some values. I already mentioned you there are using 4 displays. So each display have to display the value 0 to 9, because here I'm using 12-bit ADC. So 12-bit ADC is nothing but the maximum full scale voltage is 2 power 12 4096. So each bit has to be displayed 00000 to maximum value 4095. So in the 00000 to 4095, 4096 steps are there. So each voltage as producing any number between 0 to 4096. So now this is the potentiometer, right? If I'm moving the potentiometer, the corresponding digital value will change, right? Uh, just check. So now I'm going to move the potentiometer in the 0 position. So now I place the potentiometer in the 0 position. So 7 segment display shows the value. All bits are 0 0. Keep on. I have to increase the voltage. The value is moving. Now the digital value is 252. So you need to find out for this 252 what is the corresponding analog voltage. So you have to check it using multimeter or using the conversion formula. And I have to move the maximum. I have to move the maximum, the potentiometer, that is the mid value 2456 something. So 2400 something, it's the midpoint of the potentiometer. And then maximum I have to move, so that is 4095. So the minimum maximum voltage is 3.3 volt. For this 3.3 volt, it will be display is 4095. So in minimum 0 means 0 volt. For 0 volt, it will be display the values 0. So 0 to 4095, 4096 steps will be converted from 0 to 3.3 volt. So you have to place the multimeter in the point of the potentiometer, you will get the corresponding analog voltage, or based on the digital value, you need to convert the analog voltage. What is the corresponding analog voltage of this conversion? So that's all about the ADC of TM4C microcontroller.